Next is process and thread. So let's discuss process. We have seen the address space of one particular application. So we have discussed that address space is common only for that application. So when the application changes, the address space changes. So how that happens? So let's see that. This is the kernel mode and user mode boundary. And we have so many application. This is the upper 2 GB of different application. Let's assume that there are different kernels here. Actually, there are no different kernels. Kernel is common for all these processes, but let's assume that it is there, just for the sake of discussion. This is 2 GB. This is K is for kernel mode. And this is user mode. This is a notepad. This is Word, Excel, PowerPoint, then Hello World. This is our Hello World application. This is the CPU. CPU has CR3 inside. CR3. This is the memory, the actual memory. This is the RAM. And the RAM has different allocations for different processes. And it has the page table. This is the page table inside the RAM. So this is a page table. Let me draw the page table in a different color. This green is the page table, which is inside the RAM. Page table has three columns. These are also pages, the kernel pages. These are kernel privileged pages. Whenever a process switch happens, so whenever I switch from one process to another, for example, right now, what I'm going to do is I'm going to press Control Tab so that I'll switch to my presentation. So right now, the process which is in the focus is the PowerPoint. Right now, this is my whiteboard. What happened when I did that? What happened is the CR3 got changed. The value of the CR3 is the root of the page table, or the corresponding page table is pointed by the CR3 register. When the CR3 register changes, the page table changes. When the page table changes, the memory pointed by the virtual address also changes. For example, there is a page table translation for notepad, and there is a specific CR3 pointing to that notepad, right? Whenever the notepad CR3, for each process there is a CR3. Whenever that CR3 changes, the page table changes. When I load the words CR3 inside the CR3 register, so now I am loading the word CR3. These addresses which are getting translated using the page table will be pointing to a different place in the RAM. This is the word inside the RAM. Like that, whenever I switch the CR3, the page table changes and the corresponding translation changes, and it will always point to different places into the RAM. So which means that Notepad, Word, Excel, PowerPoint, all these processes running here, all these processes in the system points to different places in the RAM because they have different page tables, right? That is how the process switching happens in the protected mode operating system. Most of these things are true for Linux as well. Linux works exactly the same way. Now, what about kernel? CR3 doesn't change kernel. In fact, it does change the kernel, but just that the kernel pages, the kernel page table entries are pointing to the exact same translation for all the processes. For all the application, it looks like one single kernel. In fact, it is one single kernel because the PTEs of kernel will translate for all the processes. The PTE of the kernel will translate to the exact same pages inside the RAM. That's why there is only one kernel. Let me rub it off. There is only one kernel. The kernel is common to all the processes. Why? Because whenever we do the translation of the page table entries of this lower 2 GB, it always translates to the same memory in the RAM, while this entries translate to different parts in the RAM. That is how the processes are maintained inside the operating system. So next is thread. Process in the modern operating system terminology, process doesn't do anything, although the name is slightly misleading. Process is normally a name for the address space, the space we have seen, the address space. Process provides isolation for the threads, while the threads actually execute code. So threads are the ones which get CPU slices. From my definition of thread, thread is an entity in operating system which is guaranteed to execute the instruction we are giving in the exact same order. So if you are giving 10 instruction to a thread, and if it is executing that instruction in that particular thread, it will execute in the exact same order. But if you are giving 10 instruction to a number of threads, it could be executing in any number of order. Threads are used for asynchronous execution, concurrency, etc. Thread mainly has a set of register context and it has a stack. It also has call stack because it has a stack. Remember the story which I was telling, the Theseus and Minotaur? That is what the thread is all about. Thread is doing everything in a program or a group of threads. Now let's see the processes and threads in the debugger. If you go to Task Manager, or if you want, you can use Process Explorer from sysinternals. Doesn't change anything. So these are the different processes inside the system right now. So these are the different processes. All these processes has a unique address space, like I mentioned before. Every processes has a particular number of thread inside, at least one thread inside. Unless it's a zombie process, you will have at least one thread inside it. Let's start a process and let's attach a debugger. So I'm going to start a notepad. So this is a notepad. I'll get a notepad process here. There's so many notepads are there already. In the debugger, I'll go for the notepad which I started in the end. When we discuss kernel, we will get to see how the view of all this thing from a kernel debugger. Right now, we are kind of ignoring that fact. We are going to attach process. This is a notepad we have started. Now to see all the threads inside this process, the command is tilde. These are the different threads inside this particular process. So there are total 7 threads inside this particular process right now. To see all the stack of all these threads, we have seen this command before, but I am typing it again, tilde*k. This will give the call stack of all the threads inside the process. This is the main thread of this particular process and it is waiting for messages. That's how the notepad works. This is the notepad WinMain because it's a Windows application. These are the other threads of notepad. So thread has a stack. Now to see the information or more information about thread, the command is bang_teb. Bang_teb will give you a lot of user mode information about the thread. In fact, thread is not a user mode object. It's a kernel mode object. We will see much more information about this thread in kernel mode. But we are looking at user mode debugging. Thread environment block, that is the user mode data structure for every thread inside user mode. One thing interesting is stack base and stack limit. This is where the stack of the thread starts and this is where it ends. If we allocate beyond this particular address, we'll get a stack overflow exception. That is how you define a stack overflow exception. If it is above the stack limit, then we will have that problem. Now the peb, the process environment block. So bang_peb. Bang_peb has a lot more information. It has the list of loaded binaries. Then it has the command line arguments and stuff like that. Then the environment variables of this particular process, that is also is there in the peb. All these data structures you can do raw dumping. I think I have shown you this. dt, then ntdll, bang underscore teb, then the pointer. You can do raw dumping to see more information about the data structure. Same we can do for peb as well. If you do a -r, we get the recursive nested structures of the tab. So it has some interesting information like image path name, command line, etc., window title. Here we can click to dump it further. Now we can do the same thing for peb as well. First we need to get the peb pointer. For that we are going with bang peb. This is the peb address. Instead of tab we can mention peb here and then the peb address. This is going to be a little big. Again, it has way more information than we can use. Always go with bang peb unless you are looking for some specific information. So we will get some more details into this data structures when we go through. Processes are nothing but address spaces. Address space has memory allocated using page table entries, and threads are inside the process. Threads execute things. That is what we see on the stack. Process cannot execute anything. It just provides a space to execute, playground for the thread. Threads are like live objects, like human beings, if you will, while process is like a house where human beings live.